Good afternoon, everyone. I'm Ryan Honeyegger, and I work extensively on the infrastructure that supports observations in the JEDI system. And today I'm going to talk about the development of observation operators and quality control in JEDI. So by development, I mean the guts of the UFO code itself. This talk is focused on what goes where and how everything works together, and I will show a small amount of C++, but really only to illustrate a few points. In case you are unfamiliar with the language, I am giving an overview talk of C++ tomorrow morning. So at the core of JEDI is the Object-Oriented Prediction System, or OOPS. And this provides a generic interface that lets us bind our models to common generic or shared components inside the JEDI system. And these shared components include the interface for observation data access. So that's YODA, which you heard about yesterday. It also includes the system agnostic background error representation, or SABRE code, that you're going to hear about a lot tomorrow. And also the unified forward operator, or UFO code, which is what I'm talking about now. So most of the model observation interactions happen through the generic code that is written inside of the OOPS repository. And OOPS provides these interfaces that describe how a model will interact with your observations. And UFO provides all of the generic or reusable implementations of these interfaces. So it implements your observation operators, your QC, and your bias correction in such a way that different groups can customize it to actually reproduce whatever configuration they want. So instead of implementing a particular operator for a particular model, UFO encapsulates this operator and it makes it very configurable so that by writing a little bit of YAML, every possible model can use the same operator. And this regularity in the interfaces lets us add new models or instruments very efficiently. Now, UFO contains more than just an implementation of the observation operators themselves. So I'm going to walk you through some of the core features in UFO. They're shown here, starting with locations and geovals, and I'll continue through our implementation of QC. There are some other talks today and tomorrow that will elaborate more on the UFO code, particularly on bias correction, as well this afternoon's practical, but I'll leave that topic to the later presenters for time. So let me just explain how UFO works in the context of satellite radiance calculations. So UFO is not by any means restricted to this, but it is a good example. So say that you've got a model and you want to figure out what an orbiting satellite radiometer is going to see. And this really is a hard problem, but it can be broken into a couple of steps. So let's say that your model has your surface emissivity, it's got profiles of your temperature, your water vapor, your ice, and so on at a set of very precise discrete locations along a grid. And what you want to first do is you have to interpolate the data on your model grid to match the locations where your radiometer is observing. And one way to do this is hinted at in the figure on this slide, where we are just illustrating some basic multilinear interpolation of regularly gridded data. And there is more than one way to do this. But once you've interpolated in space, then we linearly interpolate in time. And this whole interpolation process is accomplished by our geovals classes, which stand for geophysical values at locations. Next, after that, we're going to apply the operator itself. In this case, we would apply the community radiative transfer model to convert the model state into a set of observables like radiances or brightness temperatures. And then, since no algorithm or sensor is remotely perfect, we apply some bias correction transformations to attain better agreement with what the simulated observations would actually see. And then finally, we do set some quality control information based on the data at each of these steps. For some reason, I can't advance. There we go. So let's break this down one by one. GeoVals, again, stands for the geophysical values at locations, and it's used to pass the model variables to the observation operator. And it sort of acts as the glue between the model and your desired observables. So you've got a model that represents state, but that model has its own system for storing data. It might be, say, an MPAST-based model, in which case your grid points are relatively irregularly spaced, or it might be something like FV3, where we've got that meshed cubical sphere. And really, again, the model has its own system for storing its data. And then you want to take the model state at certain locations, but those locations aren't the locations where the model has a grid point. So you use this geovals code to do the horizontal and temporal interpolation. And it's the first step of that forward operator. So we split this into two parts thanks to the power of loops. The first part is that model aware part. And the model aware part knows best how to properly interpolate based on the model's grids. And then the model agnostic part really is everything else. It's the interface that the operators can query to read in their data. So it's important also to emphasize that geovals represent interpolated vertical profiles of your various or of your variables at an observation location. We also don't interpolate every variable that a model provides because that would be far too much. Instead, we only specify the variables that we care about and we only interpolate over those. We want to be numerically efficient. And once we've got the geovals, then we want to calculate our observation operators. So in the context of that microwave instrument example earlier, we would want to simulate some brightness temperatures using CRTM. Conveniently, we've already implemented this interface along with many other observation operators. And for these examples here, I do refer you to Hui's and Fabio's talks today. And we use a factory pattern to implement these and to invoke them. So UFO's operation can be controlled by those YAML files that were mentioned in the earlier talks. And we construct objects in C++ space or inside of our program using what's called a factory. And you might wonder what I mean when I say a factory, or more specifically, an object factory. And from the programmer world, a factory is a type of pattern that's used to create a new object. So take this pseudocode example where you have the set of all possible computers and you want to build a computer. But say that you're instructing your system, okay, I want to build a laptop computer or a desktop computer. Each one of those is a type of computer, but you don't want to hard code in that you always want to have a laptop or always have a desktop. And this is where we tie in our code into YAML. So what a factory object is it provides a little function called a generator, and then you can just pass in a string or a bit of configuration, and then you create a new object and you just return a pointer to it. And then that object still looks like a computer. All of its functions or methods are all the same. But if you have a laptop, one of your functions might do something laptop specific. If you've got a desktop, your function might do something desktop specific. And what you can do is you can just substitute in the idea of computers and laptops and desktops for our different operators. So just applying this more to UFO directly, a little brief review of YAML. It's a way of specifying nestable key value pairs and sets and lists of data. And what's important is that we use YAML to drive these many different parts of JEDI, and really writing YAML is a lot easier than writing C++. So when we want to create an observation operator, we add in a new section into our YAML configuration files. We all tried this with the practical a little bit earlier. So just by means of explanation, this represents the new operator that we're invoking. And this ob space name here, that's just used for printing. It's used for diagnostic purposes of telling us where in the code we're logging our data. But really the key term here is this obs operator value, and then it passes through a name called CRTM. And this gets sent directly into our factory, which then creates a new CRTM object. And then when we create that new CRTM object, it gets configured according to what other options we provided later on in the YAML or in the same block. And this usually includes some paths to our coefficient files, to say our channels of interest, whether or not we have water or ozone or any other gases as absorbers, and so on. It also helps to see what these operators look like in C++. So really, when you create that new operator object, you're creating an object that inherits from this. So basically, it shares the same interface as this blob of C++. So when you make a new object, you call what's called the constructor. And what UFO is doing is it is going through its factory method, reading in your configuration values and sticking them inside what we call an ECKit configuration object. And then we pass in our actual observations themselves to this constructor function, and this just prepares the operator for use. Then later on in our code, we call this other function called simulate obs, and that's the workhorse function of the operator. So you want to simulate observations at interpolated locations. So you pass in your interpolated input quantities using the geovals class. Again, JEDI does this for you. And then your output is another data container called an observation vector. And this just stores the simulated h of x outputs. There are two other parameters that simulate obs can work with, and these include our obs bias classes. So basically, you can pass in information about your observation biases, again, through YAML configuration. And then also you can extract extra information or ancillary information from the operator, such as Jacobians. And we use what's called the obs diagnostics class to store that type of information. Jacobians are stored later on in the JEDI system, either for diagnostics or occasionally for filtering, which I'll get into in a bit. It's also important to mention that UFO implements some linear observation operators too. And linearization is important for cost function minimization and data assimilation. You can do a retrieval based on a set of measurements, and you're using linear observation operators to minimize your error. So they're implemented very similarly to regular operators. They're also configured in YAML. They go through the same procedure of being created at runtime using a factory class. And here's what the interface looks like. So I won't show it for too long. You can reference this at your convenience, but there are two things to note here. So first, we have a couple of extra functions compared to a regular observation operator. And I've highlighted these in this top red block right here. So I'll describe them in just a second. And also our linear operator can act on different variables from our regular operator. So let me just elaborate slightly. And for those first set of functions, that set trajectory function, the simulate obs tangent linear and the simulate obs adjoint function basically are used to implement trajectories and calculate the tangent linear and adjoint observables. So basically that means that we can calculate Jacobians and we can perform our work on increments. So again, we've got three functions there that are different from the regular observation operators. And if we want to do a simulation, we have to implement our linear class. Another takeaway is that we can differentiate on different variables than we otherwise use in our regular observation operators. So I just provide two examples here. So say that you're trying to do vertical interpolation. Our regular operator requests that you provide in both air temperature and air pressure. But when we're running the linear observation operator, we only are updating our air temperature. Air pressure is assumed to be completely unchanged and constant. We do something similar with CRTM. So in CRTM, the observation operator requests many surface variables in order to set up its proper simulation of brightness, temperatures, or radiances. And we can vary some of these parameters with our linear observation operator, but we can't vary all of them. Some of these variables, for example, are categorical in nature, and we can't easily adjust them with an increment. Now, what if you want to add in a new operator? And if you want to do that, we've created a handy guide on our Read the Docs website that you can follow, and I will run through this very quickly. So to make an operator, it really helps to have some test data during the development. And you'll likely need to work with us to get our YODA converters code set up to generate the appropriate observations in the right format so that you have the data files to run some tests or experiment on. Then once you've got your data ready, you can generate some C++ or Fortran, basically skeleton classes to implement your operator itself. And then once you have that skeleton created, then of course you have to fill in that skeleton with your actual logic. And then you would add in your tests for your operator. You'd build, you'd fill in a bit of more code, then you build, you test again, and eventually you would have a complete operator. And once that would be ready, you would issue a pull request. So inside of UFO, all of our operators have a similar layout. And really, we are agnostic as to the language that we're using for our operators themselves. The operator can be written in either C++ or in Fortran. If you write it in C++, you basically need a header file and you need the actual definitions for your functions, and that's it. And then if you write the operator in Fortran, really all of these interfaces are implemented in C++ in the first place. So we have to add on what are called interface functions to make sure that all of our objects or all of our data remains consistent across language boundaries. And that's its own tricky topic in itself. But basically, what happens is our C++ code calls the interface, which then reformats the data so that Fortran can see the data appropriately, and then we call the Fortran-based operator. The Fortran operator has complete access to all of our YODA system and to much of the UFO code, so it can still call the regular functions to get data and to put data. It just has to go through this translation layer. So we all have recognized that there is a lot of boilerplate here, especially if you want to implement multiple operators. So really, we wrote a script to do all of this for you. And this script is, the file is down here. You can find it inside of the UFO repository, and it's fairly straightforward. If you execute it without providing any parameters at all, you get a help prompt showing you how to use it. If you execute it with the name of your new operator, what it does is it copies a set of files and it customizes them using a little bit of Perl, and it sets up the new header files and source files, and then it also will write all of your C++ and Fortran bindings for you. So if you're using Fortran, that's great. If you're using just C++, then you can just delete some files, but still it accomplishes a lot of work in very little time. So to just reiterate here, the script writes all of the common parts of the operator, and you get to fill in all the details. So in the case of that C++ interface, you would just have to write the constructor of your code. So you just have to figure out which YAML options you care about and how are we storing the data. And then you would just have to write a little bit of the simulate obs function. If you would be, say, binding to another established code like CRTM or RTTOF, or basically something that can perform a forward operation for you already, you would just write binding code again. So you would initialize that other code, you would set up your job or your run, you'd execute it, you'd gather your results, and then you would just deallocate any shared memory structures. So you would either have to do this inside of C++ or Fortran. So if you do run our script ever, then you can see its output, and then it's made it very simple. There's a setup function where you can set up your calls to that other bit of code. There are to-do statements telling you what you have to change. And then there are, in the same file, there is a delete function which allows you to specify any of the cleanup functions that will be associated with your operator. That is required for more complicated operators where you do have to deallocate some memory. Beyond that, the script also does write some boilerplate examples to show you how to access the data and simulate the results. And again, it's just a lot easier when you don't have to write C++ and Fortran boilerplate code, and when you can just immediately get into your work. So this just removes blockers that keep you from writing your cool new science. Anyways, enough about observation operators. There are some other parts of the UFO that are extremely interesting, including the observation filters, and that's what I'm going to talk about for the rest of this presentation. So quality control in JEDI is handled through these observation filters. Just like with operators, these filters are written to be generic, and generic filters don't depend on any specific observation types and are configured through YAML. They can be applied either before or after the operator. And this customizability allows the UFO to encompass much of the pre and post-processing work that's being done in existing operational centers. There are a couple of areas where we do want to expand our capabilities in filtering, but the majority of the work is done. So a filter lets you filter data, and what that means is that it lets you change quality control flags, say to reject or retain observations, and it also lets you adjust your observation error variances. So for example, you might want to increase your error variance to basically decrease the observation weight in your analysis instead of just flat out rejecting an observation altogether. These filters have access to all of the data available to YODA and OOPS, so they really can act as a very powerful tool. And we have increasing numbers of filters that are available to UFO. We can filter based off of upstream flags. We can restrict the domain of our observations. We can filter based on the values of certain variables relative to other variables, and so on. We can compare relative errors. We can run functions off of variables. And really, the sky is the limit here. We can also extend these filters using what's called the observation function interface that I won't get into very much here, but it will let us do many complicated logic decisions. So in our processing pipeline, these filters can act both before and after the operator. And for filters that act before the operator, they've got access to all the initial observation data. So the data that directly comes in through the YODA system. And we occasionally do need to use all of this data. So as an example, we implement what's called a buddy check filter to check for paired observations, but these observations might be separated by an intervening 500 or 1,000 other observations. So we have to search through the list of all the observations that we're assimilating to find matching pairs. We have other filters that will search along ship and aircraft tracks to make sure that your estimates of height and velocity are consistent. And you can also, before the operator, filter based off of interpolated values at observation locations. So you can view all of the geovals information at a certain location. Once the operator is called, then you can run a filter afterwards, and it can use our H of X results, and it can look at our observation diagnostics like Jacobians. So that's a little bit of extra information, and we can determine at runtime when a filter operates. So if it does depend on a variable produced by H of X, for example, it always has to happen after the operator. So far, this ordering is automatic, but we do plan on expanding the code so that users have a bit more control over precisely when a filter executes. We want to support situations where one filter can chain onto the next, which chains onto the next, and where we can store intermediate results. That's in the future. So here's a relatively basic filter that checks whether variables are just within certain bounds, and it's called the domain check filter. And effectively, it takes a where clause, which is a special block of YAML that lets us set conditions for where a filter gets applied. So in this case, there are 3 variables that we're using in our where clause, and they act as screening criteria. So observations that are outside of the specified range of any of these conditions get filtered out. So in this example, we're applying this QC to some GNSS RO data, and we're filtering this bending angle variable subject to conditions specified in other variables. So the QC filter is operating on one variable, but if it fails, if this filter fails its check, we're only QCing out that one variable. We are not QCing out the entire location. We can be a lot more granular than that. Here's just a little bit of meta C++ code showing how the filter is defined. And all filters basically specialize the filter base class, which means, again, that they implement the same features and methods that filter base provides, but they might specialize some of these functions. So just like with an observation operator, we've got a setup function, which reads in our YAML parameters and figures out where we're storing our data. And then we've got an apply filter function, which does the actual filtering on our observations. And its own logic depends on our YAML configuration. The QC flag function here is a bit of a one-liner, and basically that just sets the specific diagnostic flag to indicate that we might have failed an OBS domain check. So this way, for diagnostics later on, when we want to figure out why certain observations or why we reject a certain number of observations, we can go through our log and we can see, okay, this one filter failed a specific set of observations, this next filter failed these other ones, and so on. It's really helpful when you try and replicate the capabilities of an operational system. So this domain check filter, it's not very complicated, and UFO support code works out all those complicated where masks in our YAML, and that just gets passed in through this parameter called inside. So if we are inside the where mask, inside is true. We also passed in that list of variables to be filtered. So the bending angle in the case of that example from the previous slide. And then all this code does is we just loop over every location for each of these variables that we specify. And then if we are inside or not, we set the appropriate QC flag. So really the power of these filters is that you can take very simple units of filters and you can chain them up to produce something that's very sophisticated. One final note before I close is that filters can do more than just reject observations. We do have the situations where we want to assign or inflate observation error estimates to data based on environmental conditions. I mentioned that one before, and this frequently occurs when processing radiance data. And when we want to do that, we can specify an action inside of our YAML. So our default action is to reject an observation that fails our check. Instead, we can run, say, the inflate error action or the assign error action to specify the error itself, or to multiply by a certain factor. And then we've also got this accept action, which just immediately, regardless of the previous state of that observation, just says that it has passed QC. Well, okay, so I think that I've covered a lot of the UFO structure, and UFO does a lot of things, and this might take a while to digest, but I hope that by now you've got a general idea of the different parts of the code. Between today's lectures, you should be well placed to understand this afternoon's practical and the ones later in the week. So I would like to thank you for your attention and see if you've got any questions.